Welcome back to the Explainer, everyone. Today, we are pulling the curtain all the way back on artificial intelligence. We hear about AI literally everywhere right now, but today, we're stripping away all the marketing buzzwords. We're going to look directly at the underlying mechanics, the pure, unfiltered mathematics and algorithms that actually make this whole thing work.
Okay, let's dive into this. Because when you strip away all the sci-fi tropes, artificial intelligence is really, fundamentally, just about finding patterns in the noise, right? It is not magic. It's simply math finding underlying relationships in raw data. Whether you're feeding a model an image of a cat or a giant paragraph of text, the system's primary job is to observe that raw data, extract the features, and identify structural patterns. The math is basically what bridges those abstract patterns into concrete equations that a machine can then use to make predictions.
Part 1. The illusion of intelligence. To understand how machines learn, we've got to first look at our own human perception.
Think about this. When you look at an image of a cat, neuroscientists know your eye first detects the image through the retina. That info is then transferred to the thalamus, which is kind of like a relay station in your brain for sensory information. From there, the signal travels sequentially through multiple areas of the neocortex. At each distinct level of your brain, different features of that cat, the whiskers, the pointed ears, the overall shape, are all processed. And incredibly, your brain pulls off this massive amount of sequential processing in just 1/3 of a second. It's just a phenomenally powerful layered system. But this brings us to a really fundamental question. How does a computer actually mimic this biological brilliance? I mean, if we want a machine to recognize a cat just like a human does, how exactly do we translate that layered, squishy biological processing into a synthetic mathematical system? Well, the answer lies in artificial neural networks. These are computing systems built specifically to emulate that layered structural organization of neurons we just talked about in the human brain. But instead of biological tissue, these networks use deep mathematical layers to emulate the brain's processing steps. And by the way, the deep in deep learning, it literally just refers to the fact that there are many, many layers of these mathematical operations sequentially stacked on top of one another, which of course is precisely why we need such unbelievably powerful computers to make modern AI work in the first place. Section 2. The language of matrices. Now we need to zoom into the micro-level building blocks. So, how does a computer actually take a real-world object, like a word, and feed it into those layers? And this brilliantly illustrates how we translate human concepts into math. We use word embeddings. A computer obviously can't read English, so we map human inputs into an n-dimensional vector space. Take the word banana. It might become the coordinate 2, 2, based on its letters and its category as a fruit. By converting words into these exact coordinates, the network mathematically groups banana and, say, mango into the exact same category space. It's essentially transforming abstract human meaning into calculable mathematical distances. And the exact same logic applies to computer vision too. A computer strips an image down into a raw matrix grid. If you look at a basic black and white image, pure white is represented by a 0, and completely black is represented by 255. You are quite literally translating visual reality into the strict language of linear algebra, so the machine can actually digest it. Part 3. Calculus and gradient descent. Okay, so we have our data neatly converted into matrices, but how does the AI actually learn from them? For that, we have to step into the world of calculus. The learning process is driven by an algorithm called backpropagation. Now, this involves highly complex chain rule calculus, but we can distill the whole shebang into 4 pretty straightforward steps. First, you input your matrix data. Second, the network performs matrix multiplication moving forward through the layers. We call this the forward pass. Third, the network makes a prediction and calculates its error. Basically, it asks, how far off was I from the correct answer? And finally, step 4, it propagates that error backwards through the layers, tweaking and adjusting the mathematical weights of the network to be more accurate the next time around. And it cleverly avoids redundant calculations by doing this one layer at a time, moving from right to left. So the crucial takeaway here is that backpropagation gives the network its error rate. But that raises another big question. How does the AI mathematically figure out the absolute best way to correct those mistakes? How does it know exactly how much to adjust those weights to ensure the error keeps getting smaller and smaller?
Well, it uses an optimization algorithm called gradient descent. Picture this. Imagine a ball rolling down a really hilly landscape. The peak of the highest hill is your highest error rate, and the very bottom of the lowest valley is absolute 0 error. The algorithm uses calculus to find the steepest downward slope, essentially rolling that mathematical ball down step by step until it finally settles at the lowest possible point. Once it hits that bottom, boom, the model has found its optimal weights.
Section 4. Probability in the real world. We have talked a lot about perfect matrices and exact calculus so far. But let's be real. The real world isn't perfectly clean. It is messy, it's highly dynamic, and it's full of uncertainty. So how does AI handle that? Well, this is where probabilistic reasoning comes into play. AI essentially assigns probabilities to different possibilities to navigate uncertain environments. In robotics, machines use probabilistic reasoning for SLAM, that's simultaneous localization and mapping, so they can navigate unknown rooms without bumping into walls. In healthcare, Bayesian networks model super complex factors like various overlapping symptoms to predict the likelihood of a disease rather than just giving a rigid absolute certainty. And in natural language processing, hidden Markov models help AI process ambiguous human speech. Basically, probability is what allows AI to adapt and make the best possible decisions even when things are totally unclear. Part 5. The ethics of algorithms. As we zoom all the way out from this micromath to the macro-human level, we really have to look at the societal consequences of these mechanisms. Because one of the most talked about challenges today is algorithmic bias. And keeping the math in mind, it is incredibly important to impartially frame what this actually is. Algorithmic bias is not a machine suddenly possessing a personal prejudice or some kind of conscious bias. Not at all. Rather, it is the strict mathematical result of a system being trained on flawed or prejudiced human input data. If the historical data you feed into the matrix contains inequalities, well, gradient descent is simply going to optimize for those inequalities. The machine is literally just doing the math on the data we give it. So to combat this, researchers don't just rely on good intentions. They use more math. They employ mathematical weighing scales, things like demographic parity, to rigorously review and balance fairness during system development. By actually embedding these mathematical constraints directly into the algorithm, developers and stakeholders can actively identify and mitigate biases before the AI is ever deployed in the real world. Now, what's really interesting about this slide is how it visualizes the ultimate dilemma in modern AI. Notice the inverse relationship here. On the y-axis, we have accuracy, and on the x-axis, we have explainability. Really simple models like linear regression down there on the bottom right are highly explainable, but honestly, they aren't very accurate for super complex tasks. But look up at the top left. We have neural networks. They are highly accurate, amazingly powerful, but they are so mathematically dense, we're talking millions or billions of parameters, that they become a total black box. They become almost completely impossible for a human to audit or fully explain. Which leaves us with this final thought to consider today. As these algorithms continue to grow exponentially in their mathematical complexity, how much transparency are we actually willing to trade for accuracy? Think about it. We're relying on these systems for critical things like healthcare, finance, and security. But as the matrices get larger and the calculus gets deeper, balancing that incredible mathematical power with real-world societal trust, that is going to be the defining challenge of the AI era. I hope this explainer helped demystify the math behind the magic for you today. Keep questioning the data, and I'll catch you next time.